Lecture 1. This lecture is about Chapter 1 from R.C. Hibbeler book, and the chapter title is Mechanics General Principles, and the topics covered are 1.1 to 1.6. In this video, theory portion of the chapter is covered, and in the next video, problem solving will be covered for these topics. So let's begin. Objective for this chapter is understand what is mechanics and what is statics, and mostly this chapter is primarily focused on different types of units which are used in engineering calculations and representation. So what are the different unit systems and what is the correct way of writing units and representing the answers for engineering calculations? Each presentation has also reading quizzes. Most of the time the answers of the reading quizzes are not covered upfront, but you will understand or you will find out those answers as we go through the content of that presentation. Let's for now just focus on these two quizzes. So the subject of engineering mechanics deals with what happens to a body when blank are applied to it, and there are different options here. You will get the answer in the next slide. And the question 2 is blank still remains the basis of most of today's engineering sciences, and the correct answer is, again, you will get to know that answer shortly during the presentation. What is mechanics? So mechanics is the branch of engineering where we are interested in studying what happens to a body when forces are applied to body. So study of what happens to a thing or an object or body when forces are applied to it. Now that body can be a very small, as you can see in the figure on the left side, or it can be a big body such as an aeroplane, or for that matter entire Earth or the moon. There are different branches of engineering mechanics depending on the type of the body. So if the body does not change the shape when the forces are applied to body, then we call it rigid body dynamics. When body changes shape when forces are applied, it's called deformable body dynamics or mechanics. And when body is either like the gas or fluid, then that is called fluid mechanics. Now, for the purpose of engineering statics course, we will focus only on rigid body mechanics. So anything that we consider as a body for statics does not change the shape when the forces are applied to it. Now there are two further sub branches of mechanics, statics and dynamics. Statics is when forces are applied to a body and the body does not move. At that time we can say that the speed of the body or velocity of the body is 0. Or if body moves, it moves with constant velocity. For example, the Earth rotating on its axis. So in both of these cases, if we take the derivative of velocity, that is dv by dt, then we get acceleration. So if we take the derivative in either of these cases, the acceleration is 0. Now, sigma f equal to ma is mathematical representation of Sir Isaac Newton's second law of motion, and as per that law, when acceleration is 0, that means sigma f equal to 0, and this is the foundation or fundamental equation for engineering statics. So in statics we will study all the types of problem where sum of the resultant forces is 0. That means body will have either 0 velocity or constant velocity. As a result, it will have 0 acceleration. So for the next few slides, we will talk about the different laws of motion, because statics is based on Newtonian mechanics, which is still the foundation of engineering mechanics. So there are three famous laws of Newton: first law, second law, and third law. The first law states that every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. For example, the ball resting on the ground will rest on the ground as long as no one kicks it. Or a person going on a bike will keep going as long as there is like no friction and the fuel in the bike and there is no obstacle. And as per the same principle, the Earth is still orbiting the Sun and the Moon is still orbiting the Earth. Newton's second law of motion states the relationship between the object's mass and its acceleration and applied force. So mathematical representation of that is F equal to ma. So for a mass to have a certain acceleration, we need to apply force, and we can calculate the magnitude of the required force depending on the value of mass and acceleration that we are looking for. So if we apply same force to two different objects having two different masses, that will result in different acceleration. So applying certain force to a car and applying the same force to lone mover will result in different values of acceleration. So we can see here that the length of acceleration vector is smaller for a car because it moves slowly for the same force, but the same force when applied to a lone mover, the length of the acceleration vector, which also indicates the magnitude of the vector, is much higher. In other words, if you would like to have the same acceleration for two different objects, lightweight object and heavyweight object, then we need to apply different values of forces. We need to apply less value of force for lightweight object, but we need to apply high value of force for heavyweight object to have the same value of acceleration. So that is Newton's second law of motion. Newton's third law of motion states that for every action, there is an equal and opposite reaction. So if you fill the balloon with the air and pinch the end of the balloon with your fingers, but the moment you release the balloon by opening your fingers, then the air will push out from the balloon, but at the same time balloon will move in the opposite direction. And it's actually the very same principle that's applied to rockets that go to the space. So rockets, they burn the rocket fuel inside the engine, and the exhaust gases exit the rocket with high velocity in the downward direction, and as a result rocket experiences the force or reaction in the upward direction and it flies up. If you are standing on a boat and if you jump from the boat in one direction, then the boat will travel in the opposite direction. So every action has equal and opposite reaction. Apart from these three laws, there is another law of Newton, which is law of gravitational attraction, that states that every body in the universe applies attraction to another body, and the force of mutual attraction between them depends on the magnitude of their masses and the distance between them. So the force of attraction between a big body m1 and the small body m2 can be calculated using this equation, where m1 and m2 are masses and r is the distance between two bodies, and g is called the universal gravitational constant, and its value is 6.66 multiplied by 10 to the power 11 Newton in the bracket meter per kilogram square. Now that means that the earth, if we consider earth as one body m1, and if we consider a human as another body m2, then earth also applies the force on the human. Earth attracts the human towards it. And if we substitute in this equation, if we substitute m1 is equal to mass of the earth, which is 5.97 multiplied by 10 to the 24 kilograms, so it's significantly heavy, and the radius of the earth from here to here, the distance is 6.371 million million meters. So if you substitute that, and if you substitute the value of universal gravitational attraction, then these three numbers are, when you multiply them together, then the only another number remaining here is the mass of the person. Then the multiplication of these three numbers is 9.81, which is nothing but the value of gravitational attraction or gravitational acceleration g that we define in SI system. If it is FPS system, then the value of g will be 32.2 feet per second square. So remember that the gravitational pull that we experience is nothing but the gravitational attraction by the earth on our body, and that can be calculated as 9.81 multiplied by our mass. In fact, we also call this quantity weight of the person, and for that we use the unit Newton in SI system, or if it is FPS system, we define that in pound. Four fundamental physical quantities are used in engineering unit definition, and those fundamental quantities are length, mass, time, and force. And there are two different types of unit system One is SI system or system of international standard, and second one is called FPS system or US customary system. For SI system, length is defined in meters. For FPS, length is defined in foot. Mass is defined in kilogram. For FPS, mass is defined in slug, which is not very common unit, but yeah, remember that for FPS unit, the mass is measured in slugs. Time is measured in seconds for both the systems. Force for SI system is measured in newtons, and force for FPS system is measured in pound. So remember that these are fundamental physical quantities. That means that other units are actually derived by combining these units. Okay, so this is what it has been explained here: SI system and US customary system, USSC, or you can also call this like foot pound second system or FPS system. And that's the same table about different types of units for SI and FPS system. During engineering design, we may have to convert from one type of unit system to another type. So this table has the conversion value. To convert 1 pound into 1 newton, we need to multiply pound with 4.488. To convert 1 slug into kilogram, we need to multiply that with 14.59. And to convert 1 foot into meters, we need to multiply this 0.3048. So can you convert 47 pounds into SI units? So can you convert this into newtons? You can pause the video and try to convert this into newtons. And the answer is 209.06. You multiply 47 by 4.488 and then you get the answer in newtons. There are certain rules that we need to follow when we write the units for our engineering calculations. Number one is never use plurals in unit. So if it is 5 kilogram, then use kilograms, not kilograms. If there are multiple units together, then put the period in between them. So meter, period, or dot, seconds. Most of the units are defined in lower cases except if it is Newton, Pascal, Mega, or Giga. If units are multiplied together, then you can put an exponential power to it. For example, centimeter multiplied by centimeter can be written as centimeter square, or meter multiplied by meter can be written as meter cube. We oftentimes use this unit for volume and centimeter square for area. Compound prefixes should not be used. So if we have a unit or a quantity that has that has both units in numerator and denominator, for example, density, kilogram per meter cube. So we should not use compound prefixes. That means do not use prefix in numerator and in denominator. We use only in numerator. Depending on the magnitude of the number, use appropriate prefixes to represent the unit. So if the number is more than 1000, then use kilo, mega, or giga. We are familiar with these terms because we oftentimes use them in the context of memory for electronic devices like certain megabytes or gigabytes of memory. And if the unit, the number is smaller than 0.001, then use appropriate prefix milli, micro, or nano. Like for example, nanotechnology means technology of devices having size less than 10 to the power minus 9 meters. So let's put this into practice. So let's say if the force applied is 3000 Newton, the number is more than 1000, then for engineering purpose, we will write this as 3 kilonewton. Okay, so we will use appropriate prefix such as kilo and then replace this 30 by the letter K. So this is 3 kilonewton. Or if an object has size, let's say 3 multiplied by 10 to the minus 3 meters, then we will write that as 3 millimeter. So we use prefix and then we get rid of this 10 to the power minus 3. So use appropriate prefixes in your calculation every time when you perform any engineering calculations. Next and very important step for engineering calculation is to represent your final answer up to significant figures. For most engineering calculations, we will represent our answer to 3 significant figures. So what are significant figures, by the way? So non-zero digits are always significant figures. Zeros between non-zero digits are always significant figures. Leading zeros are never significant figures, and trailing zeros are only significant if the number contains a decimal point. We will see a few examples with where each of these rules is applied. So let's look at this example that we have different numbers. Let's say these are our final answers, and we need to identify how many significant figures are there in each number. So this number has two digits, 8 and 1. So both are significant figures, 8 and 1. This number has three digits, 2, 6, and 2. So there are three significant figures, and they are 2, 6, 2. This number has 7, but it has leading zeros. And as per the previous rules, leading zeros are never considered as significant figures. So there is only one significant figure, and that's number 7 itself. This number has zeros in between significant figures or non-zero numbers. So all numbers are significant figures. So there are 6 significant figures, and they are 5, 2, 0, 0, 3, and 8. This one has 0 at the end. However, there is a decimal point, so we still consider this 0 as significant figure. So number of significant figures are 1, 2, 3, and 4, and they are 3800. This number also has 0 towards the end, but there is no decimal point. So these two zeros are not considered as significant figure. So there are only 3 significant figures, 7, 8, 8. There are 4 significant figures here, 7, 8, 8, and 0, because there is a special symbol on top of that 0. And there are 5 significant figures here because there is a decimal point, 7, 8, 8, 0, 0. So let's apply this knowledge to this example and try to identify how many significant figures are there in each example. Again, you can pause the video and answer the question. Okay, and here are the answers. So number A has 3 significant figures, 0 is not significant. All 4 significant figures, none of these zeros are all these zeros are significant figure because there is decimal point. So yeah, there are 5 significant figures. Here only these 3 are significant figures. In this example, only these 4 are significant figures. In this example, all 5 digits are significant figure because there is period or decimal sign here. And for this example, all figures are significant figures. Rounding of the answer. So oftentimes during our calculation, our answer is like a number which is not the exact number, so we have to round off. So there are certain rules for rounding up. So if we need to round off this number 3528 to nearest like 0, we will round this as 3530. Because the last digit is more than 5, we will round it to the 0 and increment the previous digit by 1. So 2 changes to 3 and the last changes to 0. When it is smaller than 5, then we round it to the lower side or downside. So for example, in this case 0.0352, so it's rounded to 2, it's rounded to the lower side when we remove this number 5. And if the last digit is exactly 5, then there is a special rule that if a digit preceding it is odd, then round up, otherwise leave as is. So we will round off our answers to 3 significant figures in engineering mechanics. And this is the final slide for this chapter, which explains the problem solving strategy. It's called IPE approach, where I is for interpretation. So that means for any engineering problem, you first read the given data, make necessary assumptions, and find out the missing information. That is called interpretation. Number 2 is plan. You think about the major steps or roadmap that you will take to solve the problem. Think about multiple possible solutions if they are applicable. And the last one is you execute or carry out your steps. So draw necessary diagrams, write down the equations, estimate your answers, round your answers to 3 significant figures, apply appropriate prefix, suffix, and represent your answer to correct units. So remember that this is the strategy that we will follow throughout the engineering statics, that is IPE, interpret, plan, and execute. Okay, and that's it for this video.